Okay, this is section 15.4. We're going to break this lesson up into two videos, right? So this is going to be part one. We're going to talk about Hess's law, mostly in this video, and how to use it to calculate the enthalpy change for a reaction. Okay, so we're going to talk about tables of standard enthalpies in part two, and also how to use the standard enthalpies to calculate the delta H. We'll do all that in part two. Okay, so we just don't have very much vocabulary here, just these two things. We're going to concentrate on Hess's law in this video. So the enthalpy for a reaction, for a change in reaction, can be calculated using Hess's law. Okay, so this is the definition of what Hess's law is, and it says you can add two or more thermochemical equations to produce a final equation for a reaction. Then the sum of the enthalpy changes for those individual reactions is the enthalpy change for the final reaction. So it's kind of, in the words here, it's a little confusing, but you can add up two or more equations to come up with the final equation that you're really interested in. Okay, so this is kind of like a graphic here. We have the synthesis of sulfur trioxide. So we start off with sulfur and oxygen. Okay, so the first reaction combines the two sulfurs and two O2s, and it makes two SO2s. Well, that's sulfur dioxide. We want sulfur trioxide. Okay, so that reaction gave off 594 kilojoules of heat. Okay, so the next reaction takes this two SO2s, adds another O2 to it, and it creates the 2SO3. Okay, so this second reaction equation D, they've got it labeled here, gave off 198 kilojoules of heat. So together, these two reactions gave off 792 kilojoules of heat. So the synthesis of sulfur trioxide from the oxygen and sulfur had an overall energy change of negative 792. So from the add up these two equations and get the delta H's for both of those to get the delta H for the synthesis of sulfur trioxide. So this is a more typical equation how it looks here. So you want to determine the delta H for the decomposition of this is peroxide. It breaks down, the liquid peroxide breaks down into water and oxygen gas. So we have these two equations, okay, and their delta H's. All right. So the first step is to match the reactants and products. We want to get these reactants and products in equations A and B to match the reactants and products in this equation we're interested in, which I have up here in blue. Okay, so we may need to reverse these equations and the sign on delta H if necessary. So I'm looking at this equation, this first equation, and the reactants are H2 and O2. That's not one of my reactants. Then my product here is two H2Os. Okay, well that matches great with the product here. So two H2Os is one of the products, two H2Os is one of the products here. So I'm going to keep this equation just like it is. I look at the second equation, and it's got some reactants that not really interested in, but it does have this over here. So that's the same as my reactant over here, but it's on the wrong side of the equation. So now I'm going to reverse that. I'm going to reverse this equation, put this product on the reactant side, put these reactants on the product side, and change the sign of this delta H. So when I do that, it looks like this, right? It's the same equation, just reversed. The products and reactants are reversed, and the sign on the delta H is reversed. Okay? So now my equations look like this, right? So the next step is to match the moles up in the desired equation, right? I have 2 moles here, so I need to put 2 here. So I need to multiply equation C by 2, put a 2 in front of all these, and I need to multiply the delta H by 2. So I do that, equation C looks like this. Okay, so then I put that together, equation A and equation C. Now I'm going to cancel out any terms common to both sides. So when I do that, I'll show you how I do that here. Do I have it on this? No, I gotta go back. Okay, so what I'm talking about is that we look at the things that are on on the equation A, we have H2 and O2. I don't really want the H2 and the O2. So I look for two H2s. I want to eliminate that. Do I see a 2H2 on the product side? Yes, I do. So I can eliminate this two H2s because I have one on the reactant side and one on the product side. Same thing for the O2. Can I eliminate that? Well, I want to eliminate this one, but I want to keep one of those there. So one on the reactant side, and I'm going to eliminate one of these two on the product side. So now I've got on the reactant side, the only thing I have left is 2H2O2, which is what I want. Okay. And on the product side, now I have two H2Os, which is what I want, and I'm down to one O2. Okay, so that's good. That's what I wanted to have happen. This, to get the delta H, is now you just add up the delta H's here, the negative 572 and the 376. My delta H for this reaction is negative 196. Okay, so this is another example of Hess's law where we want we want to get this going from these two equations. Okay, so I'm going to go through the same thing. I match reactants and products. So I look at equation A here, and I've got two CO2s in the reactants. That's good. O2s, don't care about that. That's not in the reactants. I'll just skip that for now. The two CO2s, those are in my product. So I'm going to keep this equation just like it is and probably eliminate this O2 some other way. Okay, so then I look at equation B. Okay, so these reactants and these products are on the wrong side, right? I need the two NOs to be on the reactant side, and I need the N2 to be on the product side. So I'm going to switch the this equation around. So when I do that, reverse it, the two NOs are on the reactant side, and the N2 and the O2 are on the product side. The N2 and the two NOs, that's what I'm interested in. Those are on the right side. So now I've got everything on, I got the products and the reactants, and I'm looking for ways to do that. So checking the moles, do my moles match? Yeah, the 2 matches there, the 2 matches here, the 2 matches on the CO2s, and 1 N2, yep, so my moles match. Okay, so I cancel out any terms common to both sides. Okay, so I'm going to go, this is these are my two equations, my A and B. So if I add up all the reactants, two CO2s, O2, two NO2s, I get those three things on this side. And on this side, I've got two COs, N2, and an O2. Okay, so what do I want to eliminate? The things I want that are the same on both sides. Well, this O2 and this O2 are the same on both sides. Okay, when I eliminate those, I have the equation that I want. I've got this is the exact equation I'm looking for. So the delta H's, I'm just going to add up those delta H's, and the delta H for this reaction is negative 385.4. Okay, standard enthalpies, heats of formation. I'm going to leave that to the next video. I just wanted to concentrate on Hess's law on this one.